Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to cover the 2 norm for finite dimensional vectors. So in this topic, we will define the 2 norm for finite dimensional vectors r to the n and c to the n. We will define the distance between two vectors using this norm, and then we will describe the properties of the 2 norm. We will define the 2 norm of a vector in the finite dimensional vector space of n-dimensional vectors with entries in the field F as being the square root of the sum of the squares of the absolute values of the entries. The subscript 2 next to the 2 bars indicates that this is the 2 norm. Notice that if u is an element in r to the n, then the 2 norm is simply the square root of the sum of the squares of the entries squared. The absolute values are not necessary. If u is a complex n-dimensional vector, then we can calculate it by calculating the square root of the sum of the complex conjugate of the kth entry times the kth entry of u. For example, if u is the following vector, then the 2 norm of this vector is the square root of 3 squared plus negative 6 squared plus 2 squared, which is 9 plus the square root of 9 plus 36 plus 4, which is equal to the square root of 49, or 7. On the other hand, if we have this complex vector here, then the 2 norm is simply the sum of the squares of the absolute values of the complex numbers. So the absolute value squared of the first complex number is just 3 squared plus 2 squared. The absolute value of the second is negative 1 all squared plus negative 3 all squared. And the absolute value squared of the last is negative 2 all squared plus 3 squared. This works out to the following sum, which is equal to the square root of 36, which is equal to 6. So the 2 norm of this vector here is 6. That is how long it is. Now, sometimes we will just write the vector with the 2 norms bounding it, and this again will denote that we are calculating the 2 norm of this vector. So in this case, this is equal to the square root of this sum of real numbers, which is equal to the square root of 44.89, which is 6.7. By the way, normally they don't work out that easily, but in this case, it actually does. Now, why is it called the 2 norm? The 2 here refers specifically to each entry being raised to the power 2. Now, most of our examples have been with 3-dimensional vectors, but nothing restricts this to 2 or 3 dimensions. For example, here we have a 5-dimensional vector, and we can calculate its 2 norm by simply summing the squares of the entries. So in this case, the 2 norm is the square root of 2.89, which is 1.7. Next, we will define the distance between 2 vectors u and v as being the 2 norm of the difference between u and v. Recall that u minus v is the vector that is equal to the vector starting from v and going to the vector u. Now, what are some of the useful properties of the 2 norm? Well, first of all, notice that the 2 norm squared is just the sum of the absolute values of the entries all squared. Well, each of these entries in this sum is greater than or equal to 0, and so therefore the 2 norm squared is greater than or equal to 0. If we take the square root of both sides, we get that the 2 norm is greater than the square root of 0, which is 0. All right, so that's our first interesting property. The 2 norm is guaranteed to be 0 or positive. Second, we see that the 2 norm of the 0 vector is indeed 0. Finally, if u is not the 0 vector, then there must be some entry u sub l within the vector so that which is not equal to 0. Therefore, since we have a sum of positive values, then that sum will be greater than any one entry in that sum. So specifically, we know that the 2 norm squared is greater than or equal to the square of the absolute value of the entry u sub l, which is assumed to be non-zero. Therefore, the 2 norm is greater than or equal to 0, and the 2 norm is equal to 0 if and only if the vector u is 0. Third, what is the 2 norm squared of alpha times u? Well, alpha times a vector u simply multiplies each entry of the vector by alpha. So the 2 norm squared, which essentially gets rid of the square root, is just the sum k going from 1 to n of the absolute value of alpha times u sub k all squared. But wait a second. Alpha times u sub k is the product of 2 real or complex numbers, and in either case, the absolute value of a product is the product of the absolute values. So now we have a sum where every single term in that sum has a common factor. So let's bring the absolute value of alpha all squared out of the sum. Oh, wait a second. The sum that remains is just the 2 norm of u all squared. All right, so we have that first term equaling the last term. As they are both positive, therefore the square root of the first term equals the square root of the last term, and the square root of the product of 2 positive numbers is the square root of each of those, and therefore the absolute value of, or the 2 norm of alpha times u is the absolute value of alpha times the 2 norm of u. All right. Finally, recall that for complex numbers, the absolute value of the sum of 2 complex numbers cannot be greater than the sum of the absolute values. I cannot have 2 complex numbers that have absolute value of 5, but when they're added together, we get a length of 25. No, the maximum it would be is 10. Well, the same is true for the 2 norm. If we sum 2 vectors, the 2 norm of that sum cannot be greater than the sum of the 2 norms of those 2 vectors. So the 2 norm of u plus v is less than or equal to the 2 norm of u plus the 2 norm of v. Thus, the recognized useful properties of the 2 norm include the fact that the 2 norm is greater than or equal to 0, and it is equal to 0 if and only if u is the 0 vector. The 2 norm of alpha times u is the absolute value of alpha times the 2 norm of u, and the triangle inequality. Now, let's go back to the definition of the distance. First of all, if u is equal to v, then u minus v is equal to the 0 vector. Consequently, the distance between u and v is the 2 norm of the 0 vector, which is equal to 0. On the other hand, if u is not equal to v, then u sub l must not be equal to v sub l for some l. We're not sure which one, but this must be true for at least one of the entries. Consequently, u sub l minus v sub l is not equal to 0 for that specific l. Therefore, u minus v is not equal to the 0 vector, and therefore the distance between u and v must be greater than 0. So, the distance is equal to between two vectors is equal to 0 if the vectors are equal, and if the vectors are unequal, the distance must be strictly greater than 0. Might be small, but it's not 0. Finally, the distance is symmetric. Notice the distance between v and u is equal, by definition, to the 2 norm of v minus u. Well, recall from our previous studies that v minus u is equal to -1 times u minus v. We proved that a few lectures back. But wait a second, this is the 2 norm of a scalar times a vector. That means we can factor out the scalar. And the absolute value of -1 is 1. So therefore, that is equal to the distance between u and v. Therefore, the distance between v and u is equal to the distance between u and v. Good. We'd sort of hoped that would be true, but at least now we've shown it. So, now following this topic, you know the definition of the 2 norm. You're aware of some of the properties of the 2 norm, and you know the definition of the distance between two vectors using the 2 norm. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!